I think it's just about 1:15, and it's time to begin our lecture event. This is now the 9th in the series, unless I've counted wrong, of the Helsinki Distinguished Lecture Series on future information technology. And today we have our speaker, Wojciech Szpankowski, and it's a great pleasure for me to introduce him giving the talk today. To say just a few words about Wojciech, he graduated from the Gdansk University of Technology with a PhD, and then since that he's held various positions in mostly in the US, but also visiting positions in Europe, Paris, where he's now coming from on his road. And he has also done a lot of industry collaboration with Hewlett-Packard and other relevant companies. He's a fellow of IEEE and the Erskine Fellow, and he's a 2010 recipient of the Humboldt Research Award. And he's published very extensively. I was looking at the list, and there are more than 100 journal papers, hundreds of conference papers. There's a very kind of well-read and liked book also at our department, the average case analysis of algorithms on sequences. And I just heard from Wojciech that there is going to be another book, maybe this year, maybe later, maybe next year, on something related to Twitter and pattern matching and whatnot. He may want to say something about that. He's here not only in the role of a scientist, but also in the role of a person who's director of a center which is focusing on information theory and information science more generally. And this center is a 5-year NSF funded project involving Purdue, Stanford, MIT, Berkeley, Princeton, and a number of other universities. And they have on their roster even a Nobelist, I think at least one, and people such as the Nevanlinna Prize recipient Peter Shor, who is of course famous for the factoring algorithm. So we'll hear from Wojciech hopefully both science and and also some words that are of interest to people, directors and maybe future directors of various units. So with that, I'll give the floor to Wojciech, please.
Thank you very much, Teemu. I really appreciate the invitation. I'm very happy to be in Helsinki. Actually, I'm very happy to speak in this auditorium, Alfred Auditorium. He was a great Finnish mathematician. I think one of the first recipients of Fields Medalist. And in fact, I learned complex analysis from his books. And it serves me well, and I encourage everybody to look at these beautiful books. I want to talk today about the center, about research actually that is being done in the Center of Science of Information, which is the NSF STC Science and Technology Center. After a few general remarks and trying to tell you a little bit about the vision, I want to go into some research area that's being done in the center. I probably won't finish everything in 45 minutes. I will stop at some point, but I give you an overview, and I will be happy to entertain question and discussion after the talk. So the center is an extension and direct continuation of Shannon's work beyond, or Shannon legacy, beyond its original objective, which was to create a foundation for transmitting and storing data, for reliable reproducing data. In 1948, Shannon wrote his paper, A Mathematical Theory of Communication, which paved the way the incredible technological advances in telecommunication and storage from DVD, iPod, internet, and so on, as well as some design driver like universal data compression that is used beyond data compression, for example, in bioinformatics and extracting knowledge. But in nowadays, information is not only communicated. It's actually organized, aggregated, managed, processed, valued, analyzed, abstracted, name it. And in order to continue Shannon legacy, we need to understand flow of information in today's more complicated technologically world. And science of information is an attempt to do it. Actually, I used to say that we cannot leave information theory to information theorists because it's too important, and in order to meet today's challenges in new fields like biology, economics, data science, knowledge extraction, physics, and so on, we need to extend our knowledge and to study certain aspect of information that was not actually deeply analyzed before. In particular, the center concentrates on 4 or 5 new aspects of information: structural information, spatial information, temporal information, semantics, in a dynamic environment with limited resources, energy on the receiving side. Think of a human cell that has to do very complicated things with a limited space and also with limited energy. Think about your cell phone that has only limited energy and has to do a lot. So how actually limited energy influence the flow of information is one of the aspects that we would like to understand. We can view, at least we view, science of information as 3 bubbles. The first bubble is foundation. It's what information theory, what Shannon did, trying to understand what information, how information is transmitted, processed, and so on. But in order to do it, we have to actually deal with the right application, so we have a two-way street from application motivates our study, fundamental analysis, understanding of information, vice versa. The 2 bubbles that are important for us, one is we call data, because we are dealing with data every day and would like to understand and change a little bit the objective of Shannon, not all about transmitting, but extracting knowledge information from data. How do I know that when I query Google database or any other, that the answer I'm getting is the best possible answer from the database that I'm dealing with? So the data sciences is one application, and we would like to understand and ask a few fundamental questions in this area, and I will show you today 1 or 2. One of the application areas that's becoming and is very important and very well done here in Helsinki is life sciences. Because here, information actually, you can see information in action. And you can see these 2 bubbles overlap. Data sciences has important implication in life sciences and vice versa. So I will be referring to these 3 bubbles when I will try to explain to you what we are doing. We're in the process of the renewal. And when thinking about this, I would say that the main theme of the center now and especially in the future is I would call from data to information to knowledge. These words are very loaded words. I think there is no much disagreement what data is, but I feel quite comfortable to give you a definition of information. But please ask questions at the end, because otherwise we'll never finish it. Everybody might have his, her own definition of information. But actually, information is a measure of distinguishability. Let me repeat. Information is a measure of distinguishability. And of course, the devil is in details. You have, depends on how you define distinguishability. Shannon defined it to distinguish signals. But we can define it many other ways. The economists will define a little different. They bring into the picture value of information. And knowledge, that is too general to define, so we narrow it basically. We say knowledge in our understanding is information in action, actionable information, so it's basically applications in, let's say, life sciences. Now, many centers are trying to do it and are doing this. What is the difference? What we are trying to do differently than most of people in machine learning, data mining, and others. We actually would like to frame the foundation. Ask, after Shannon, in the Shannon spirit, try to ask the right question. Eventually, later, we try to answer them. But formulation of the question, fundamental question, as 50 years ago, Shannon asked, what is the minimum description length of a file? And how many bits I can transmit in a reliable fashion over a noisy channel? These are the questions that we want to ask for in data, information, and knowledge. And here, when theory and practice do overlap, this talk will be more on the theoretic side, but most of the definition and research that is being done is actually motivated by concrete problems. And actually, this forces us or directs us what kind of research we want to do. Let me say a few words about the center, only 1 or 2 slides so you have the idea, so I have more time for actually talking about real science. The center consists of 11 universities from east to west. In the US, Princeton and MIT, Purdue is the lead, Urbana-Champaign, Texas A&M, Berkeley, Stanford, University of California, San Diego, and we're adding Hawaii University. We have about 40 faculty from these universities, and each university is represented quite well, actually. As Temu mentioned, we have one Nobel Prize, Chris Sims in economics. He got it 2011 when the center already was in existence. We hardly can get credit for it, but we do. And we have several members of National Academy of Engineering and Science. The center mission is actually to advance science and technology through a new quantitative understanding of the representation, communication, processing of information, biological and engineering problems. The research mission is to create shared intellectual space for collaboration and for asking questions that later in the center we try to answer. Maybe at the end, if there's a question, I'll tell you how we try to accomplish it. Now, if you remember the 3 bubbles, we divided our research into 3 thrusts. Information communication, fundamental thrust, knowledge extraction, data sciences, and life sciences. These are the thrust leaders. They organize workshops and so on, and lead the discussion. Okay, so this is a few words about the organization of the center, but the most important is what science we are doing there. And I would like to show you a few examples. And again, the 3 bubbles: fundamentals, data sciences, and life sciences. So let me start with the question that I actually started the discussion: what are new aspects of information that we need to understand? One of the first is structural information. Here I have an example of a protein structure. Here some chemical molecules. Here the organizational structure. How many bits are embedded in the structures? On how many bits do I need to describe them? These are not actually the question that I formulated. In 2003, Frederick Brooks in JCM paper, I think the title was 3 Great Challenges of 50-year-old Computer Science. The first channel, he said, Shannon created beautiful theory, but he did not gave us theory of structures. So that's what we would like to understand. And I tell you a little bit what I did with my student and trying to fill this gap. Once we do fundamental work, then there are biologists and computer science applying it in bioinformatics, as well as others in social networks, trying to understand how much a substructure of social network informs another substructure or some functionality in biological network. So let me motivate this problem. Here the structure. And the first question, you want to know how many bits do you need to describe it, or how much the structure informs us. In real life, the structure is a little more complicated because it has labels. And these labels are actually locally correlated. I gave you an example here. You can see 3 towns in Finland, and the common part is Finland. 3 times in France, 2 cities in Poland. How many bits do you need to describe it jointly, structure plus correlated labels, usually locally correlated labels? I don't know the answer to the second question, but I will tell you today the answer to the first question. If I don't have labels, I have just structure, how many bits do I need to describe it? But in real life, you are dealing with much more complicated structure. It's a combination of different structures that we learn in computer science put together. This is an example of protein-protein network that is annotated by some, let's say, some gene databases. So you have a tree here with labels being sequences, but this tree, everyone, they are actually connected through an acyclic graph with an additional annotation. I call it a multimodal data structure, many different data structure in one. And the question is, of course, what is the minimum number of bits that I need to describe it? Or how much it informs me about something that, let's say, functionality in biology in this case, but something like this might look financial transaction or whatever. So what I'm gonna do, I will answer to you today a question: how many bits do I need to describe a structure like this? So let me start. And here I show you to formulate the problem mathematically precisely. Let me start with a simple 3-node label graph first. So you can see I have 8 different labels, different label graphs. But we, I think, agree that all of these 3 label graphs have the same structure, unlabeled graph, the same here, the same here. So out of 8 label graphs, I have only 4 structures. And the question that I want to ask is about this. So we learned from Shannon that entropy is, in some sense, describes the lower bound for the compression structure, including, because I can represent it in one way or another. The problem is that probability of this structure is actually probability of one of these graphs times the number of label graphs that lead to the same structure. I call it N sub S, the number of label graphs that have the same structure. Then I have 2 entropy. This is a bad name, call it label graph entropy, not kernel graph entropy. But I really need to understand the behavior of this quantity, not this one. This is easy. If I have, let's say, Erdős-Rényi graph, which I generate this way, I take n nodes, I pick any pair of nodes, and with property P, I put an edge, H. Then this entropy is basically n times the entropy of P. Very easy. But this is much more complicated. So let's try to understand why. And this picture probably will explain everything. So if I ask you how many different label graphs lead to this structure like this? The first natural answer would be 5 factorial, 120, because I permute all of these labels, I'm getting the same structure. But that's not the answer. Because there is a symmetry here, some symmetry in this graph that's causing some troubles. When I flip B and C and D and E, I'm getting the same adjacency matrix. It means the same graph. Graph automorphism is an adjacency preserving permutation. So if I permute this and preserve adjacency, which means my adjacency matrix is the same, that is automorphism. And the automorphism group, in fact, and the size of the automorphism is important. Very often, a graph is asymmetric if the automorphic group consists of a trivial permutation. But in this case, the automorphic group cardinality is 2. So n of s, in this case, 120 divided by 2 is 60. So if we go back, I want to compute this one. And remember, PS is a product of these two things. I have to understand this quantity. Then there is a simple relationship between structural entropy and graph entropy that I know how to compute. This is the quantity of interest and quantity of troubles, because I have to understand for a randomly selected graph from assembly of graph, what is basically expected number of log of the number of automorphisms. And this is a difficult problem. For Erdős-Rényi graph, let me repeat it how it works. Take n nodes, pick up 2 nodes, and put an edge between them with property P, or not an edge with property 1 minus P. This is the simplest graph generation model. In this particular case, it can be proof that the graph is asymmetric with high probability. What does it mean? That with high probability, the automorphic group is consisting of one element, trivial permutation. If this is 1, then you can see these guys go the way. Stirling formula gives me the following, that is n choose 2 HP, so grows like n squared. Another term is n log n. N is the number of vertices. By the way, this is the probability that if I randomly select one structure, this structure will have this, and this is called asymptotic equipartition property for structure. Okay. So this is mathematics, you can say. But information theory actually does more than this, and Shannon also told us this. Okay, I know right now what is my lower bound, but the second part, the converse to it, is to construct an algorithm that I can prove achieves this lower bound. It means I can't do much better if I have it, at least for a class of algorithms, generation of graphs. And that's what I will do it, and I will show you how to do it by a small demo. So here's the graph. I put labels because I need to explain it. I will store it in 2 strings, binary strings, and I show you how to do it. I choose randomly one node, I, and then I will store in string C1 the number of neighbors, not labels of neighbors, the number of neighbors. So in this case, 4. Then I'm going to delete I, this node, and all the edges, except that before I will choose another guy, neighbor. In this case, I choose F, so let me do it. I choose F. as my next stepping stone, and I do the same. I will store the number of neighbors or non-neighbors, the whole graph, which means it will go along these two sets. By the way, what I will be constructing here is something that is of not much importance for you, but it's very important for us when we analyze it. It will be a tree, something in between trie and digital third tree that we have to analyze in order to prove that the length of these two strings is actually matching the lower bound. So what I do, now I store neighbors. These are the number of neighbors here and here. And I will continue this. Now I do quicker. At some point, I have single edges. When I have it vertices with single edge, then I will store it in another string for analysis point of view, because I basically know that this sequence behaves like a memoryless source with probability P. So let me do quickly now. So at this point, this is, let me go to the next slide. Forget about that part. I concatenate these two strings. I put it through arithmetic encoder, Lempersieve, any entropy encoder. And what I can prove for such an algorithm, here's the lower bound that I showed you before. I can prove that my code length matches the first term and the second term, and it's of the same order in the last term. Now, why is it important that I try to match the second term? Because everybody can create an algorithm to match the first term. How you do it? You take the adjacency matrix, you read it row by row, and apply Lempersieve. You're going to match this first. And actually, it is important because when we apply our algorithm to graphs that do not satisfy the assumption that I make for analysis, Erdős-Renyi, they are rather power law graphs, they are actually doing very well. 20 to 40% better than that arithmetic encoder. And we know that it's provable optimal, at least in the sense that I just described to you. Why they are much better if this term is n squared and this is n log n? Because most of this are sparse graph, and p here, probability p is not constant, behave like log n over n. Then these two terms are almost the same. One grows like n log square n, the other like log n log n. That's why this matching the second term is important. Okay, I do not have a proof that this table, this theorem does not prove this table. So we have some work to do. First of all, to extend this to extend our analysis to non-Erdős graph, so we can prove actually use it to real structures. This turns out to be mathematically complicated. We have some proofs already for preferential graphs. But more importantly, I didn't tell you anything how to jointly compress structure and correlated labels. And actually, nobody knows. There is a recent paper by David Alder that is trying to understand it, but this is our next work. More. In many applications, we are interested in approximately describing the structure. So we need lossy Lempersieve, S-zip, we call it, structural zip. We don't know how to do it. We have some ideas. And finally, how to do it for multi-structural data in the sense of Shannon. First get the lower bound, then design an algorithm that achieves it. We don't know how to do it. So this is what we want to go. So I finished this part. I don't have much time, so let me go. Security. I will now tell you a little bit what P.R. Kumar designed a completely approach to security. I work in performance evaluation 20, 30 years ago. We designed a beautiful algorithm protocol that actually gave us throughput and delay. The problem is that these days, when you read about network in a newspaper, it's about security, breaching security. And there are plenty of different attacks that you can read in newspaper. And for everyone, what you do, a good software engineer design a patch, patching it, doing a little bit here and there, and solve the problem until the next attack will come. So there is no guarantee for security. So P.R. Kumar suggested that we need a new approach, clean slate approach, put security first, performance evaluation second. And in this part, I will not tell you anything about the solution. I only tell you formulation of the problem. You have to go to Kumar paper to read a little bit, and his student. So what he is saying is the following. Let's assume that the network that we're dealing, he mostly deals with wireless, satisfying certain properties, which is realistic and real. And then, if you think for a second, who are the players in security? We design protocols, and bad guys go to some nodes and make this node bad. These bad nodes can flood the network with many useless information and so on. So you have to interplay between protocol that you can design and bad nodes. It's like Byzantine agreement. Byzantine generals can do they can do whatever bad thing they can do. They know everything about the network. While protocols have limited capability of understanding what's going on. So the way Kumar formulated the following max-min and then min-max optimization. I want the best protocol for the worst possible behavior of bad nodes. And actually, he managed to prove, first of all, saddle point, but it's not importantly. He assumed only cryptographic primitives, and there is a very nice clock and synchronization problem. But his basic solution, which you have to read more carefully in his paper, is that first of all, there exists a solution to this problem. U is a utility function, delay throughput. And you mostly have to deal with jamming. But I'm not going to spend more time on this. I gave you the idea of, again, asking the right question to the old problem and trying to start pushing for a solution. I referred you to Kumar papers. So these are two results in fundamentals when we try to formulate the problem without a particular application at the beginning. First solve the fundamental question, build the foundation, then go to application. Data sciences is being done by everybody in every place. And we would like to contribute to this by actually trying to maybe formulate few questions, solving them, maybe to algorithms, and maybe not only big data, but also small data. So let me tell you first why information theory did not contribute so much to data sciences. Information theory assumed from the beginning a rather simple, if not simplistic, model for data generation. Memoryless, Markov, maybe stationary processes, but real data are much more complicated. Not only they are large and noisy, but they are dynamic, temporal and spatial. They are heterogeneous, distributed, has complex structural dependency. So what most people probably observe, that ad hoc solutions do not scale, but there is another statement from a journalist, Financial Times, John Hartford, who say big data has arrived, but big insight have not. And we would like to work on this big insight. And I show you two problems that I think the formulation is important. This is done by Tsachi Weissman from Stanford and Tom Curtey, who was a center postdoc, right now is in Berkeley. First of all, forget about the original objective of Shannon, reproducing data. I want actually to answer queries in the best way I can and have assurances that the answer I'm getting is the correct one. Okay, two problems. Let's say you have a recommender problem and Netscape comes to you and say, I want to invest $10 million in a new recommender system and I would like to profit $1 million from it. And you do your computation on the back of the envelope, you tell them, sorry, you can't get it. It is unrealistic. Because there is a fundamental limitation how much you can get. Why? Because the data that Netflix and everybody else is dealing, data are incomplete and distributed, and there is a limited thing that you can do it. So what Netscape would like to do, you would like to get the best profile of you, the best probability of each user, and use it to design the algorithm that match as much as possible to your profile. Here are users. They are distributed. Imagine that you have on the left side a huge distributed matrix of preferences. Each row is a user. And this matrix is pretty incomplete. For some people, you have pretty good information. For some, like me, I don't fill up any of this nonsense. So they have nothing about me, basically. And based on this, you have to, on the receiving side, guess the probability distribution of the distributed incomplete system and try to, in this case, what my colleague did, optimize log of the inverse of the probability to get the best estimate and to actually the best gain profit. Here's another problem. You have a huge database. It's pretty complete. Say all DNAs of all of us, but we don't want to reveal it to everybody. However, often when a new DNA comes in, you'd like to know whether this already exists in the database or not. So what's happened often, by the way, this database might be incomplete too, but what happens often, you do not have access to your database. You have to some signatures, some information about it. Think of this as a cache memory that can contain only few DNAs. So when you ask the query, is there an entry similar to Y? Y is a new entry. In this database, you're asking actually this, which has only partial information about that database. What you would like to have, when you answer this query, you would like to have the correct answer with high probability. So the question that you really want to know is how much information I need to have here, how many bits do I have to have here to answer my query with high probability? Or in other words, how few bits I need to have a query answer with high probability. These two problems are formulated in information theoretic model, very successful. The first one is multi-terminal source coding problem under logarithmic laws. This is technical math. This was actually the holy grail of information theory. But these two guys solve it. The other one, it is called quadratic similarity queries on compressed data, because this small signature could be viewed as a compressed data. So the techniques of rate distortion and compression are used to answer this question, and actually Google is sponsoring this research. Again, the solution here were technically very complicated, but I would say formulation were at least that important. I have a little more time, so let me go to the next topic. What about small data instead of big data? What about Twitter? 144 characters. And I would like to do automatic classification on Twitter. So when Twitter comes in, I look at it and say, okay, this is about politics, this is about science, this is about sport. There is a way to do it, and there's a joint work, by the way, with my colleague Philippe Jacquet. and his student Dimitrios, they are located in Paris, Alcatel, Lucerne Alcatel. So when I have two small strings, I want to know how close they are, how similar they are to DNA or to tweets or Twitters. The thing that we would like to apply is we call it the join string complexity, what it is. Okay. So take two words, X and Y, banana and ananas, and list all common subwords to both of them. You expect if two words are exactly the same, the set will be large. If they are very dissimilar, the set will be small. I'm not interested in this. It is too complicated. I'm interested only in one number. What is the cardinality of this set of common subwords? And it could be small. Actually, it would apply to tweeters. But in order actually to have some reliability in your answering and making sure that you are not basically trying to guess your solution, you need a very precise analysis of this problem, which is very complicated. So let me tell you, and here's, by the way, complex analysis, and Lars Aflos help a lot. And actually suffix tree that you are doing in this university so well. So here what I will do, I want to apply it to text. For example, I have two texts, one text of no, let's say, Polish author, poet, and I got another one, and I don't know who wrote it, so I would like to somehow classify it, whether it is the same as the one that I have at hand, or maybe different. And this kind of problems happen very often. So I will deal with text. English, Polish, Finnish, all of them are well described by Markov or higher order. So I assume that both of the strings are generated by Markov. P is probability of transition, pi is stationary, and I want to estimate the average join complexity. I generate two strings randomly by a Markov source, and I want to know what is the number of common words. Okay, this problem is difficult, and I will explain to you, and you understand. Those of you who are doing suffix tree, and most of you are doing here suffix tree, here's the problem that I can formulate it. Take a word and build a suffix tree of this word. Take another word, white, and build a suffix tree of these two. Then overlap these two trees and find the common edges, the number of common edges of these two. Analyzing a suffix is a very complicated problem. I did in '93, and it was the first analysis, actually probabilistic analysis, that are very complicated dependency. Analyzing two suffix trees with overlap over a Markov source is really a challenge. But today, complex analysis help us, and there's this unreadable slide, so I explain to you basically the following. We were able to prove that the growth of join complexity like n and the size, common size, to some exponent kappa. This kappa depends, it's an eigenvalue of very complicated matrix that you don't need to know. But this kappa has a very important property. Kappa is smaller or equal than 1. It is equal 1 only when both strings are generated by the source, by the same source. So if I write something and Temo writes something, we have a different style, so we have different, our sources are pretty much not the same, different. But if you have generated by the same source, for example, this tweeters about sports or something like this kappa will be strictly smaller than 1. So what we can do? Here we compare English to some languages, Polish and Finnish among others. You can see sub-exponential growth. This is Polish, this is Finnish. Finnish is not English, that much I know, and Polish is not English, that much I know too. And this is the proof, actually, and it tells me that if I have two texts that are not generated by the same source, they actually, you can discover it by actually seeing how it grows within, either sublinear or linear. Moreover, my colleague actually applied this to classification of tweeters, sports, politics, and so on and so on. And actually, they won, I think, the third award in some competition, so it actually works. Good analysis, precise analysis, and good programming actually, in this case, pay off. Do I have 2-3 more minutes? OK, so let me finish one in life sciences example, and then I will be done. So this is the knowledge, information and action. And again, I will look at the old problem that David Tse, right now in Stanford, he was in Berkeley, reformulated it nicely and actually asked first, in the spirit of information theory of Shannon, ask first the right question and then build algorithms. So it is DNA reassembly problem, very simple problem. You have DNA, a genome of 10 to the power 9 symbols, base. You cannot read it. You have to cut it into small pieces. So these are reads, many reads. Of length, let's say 100, and many of them 10 to the power 8. So the total number of reads, if you put it 10 to the power 10, so 10 times more than the genome. Because what I can read a small read, there are so many and overlapping that I want to make sure that I have enough of them that they cover the whole genome. How many of them? That is the first criteria that I have to actually understand. I want to find a relation between length of the read and number of reads such that I can reconstruct the genome with probability 1. No ambiguity, only one exact one genome. I do not like to have from this read a situation that there is a certain part of DNA that when I swap, still my DNA, my reads will support these two answers. I want only one answer. So here's the question that David asked. Given statistics of the genome, for what read length L and of number of reads is reliable reconstruction possible? Once you find this fundamental limit, then you would like algorithms that were produced before that reach this fundamental limit. So by the way, that's what this blue area is, what is reconstructible. So by the way, this is N over N coverage. N coverage is the minimum number of reads that cover the whole genome. It was done by Waterman and Ladner in 80s. But there is another limit on the right about the length, which again, for those who are doing stringology here, is easy to explain. So take a string of length N and look for the longest substring that has another copy inside the string. That is nothing else than the height of the suffix tree. And that is approximately high probability 2 over Renier entropy times log of the length of the string. Now, once you have it, this is the limit that David produced. Now you can create many algorithms that achieve this limit. For example, they were able to prove that greedy algorithm actually is asymptotically optimal for very large G of order 10 to power 100. But in practice, not that well. So what they did, they look at the real data. And your real data is neither generated by Markov or memory-less. It has long tail, a lot of repetition, as you know, in DNA, they are there. So they start playing, and for real data, they actually find a better and better algorithm that approximates this limit. That's what we need to do. And once I have this limit, I have a yardstick which I would like to achieve. Let me stop here.
of questions for Wojciech, and I would ask people to ask their question to the mic. We'll get the question on the audio as well. So, questions.
Over there. Work.
Okay. Thank you for your talk. It was very interesting, and you talked a lot about data and analyzing it and studying it. And in fact, I think that there is a kind of a paradigm shift in science with respect to data. But there's one question where I would like to ask your opinion, because you have this center, and you obviously are in possession of access to a lot of data, but there is one kind of new data which is only in the recent years, which is maybe the biggest of all. It's the data which is owned by private companies like telecommunication companies, Google and NSA and such things. And from the point of view of science, we scientists, we don't have access to that data. And so should we go to work in these companies, or how do we compete in this data science when some people are sitting on the data and we can't get to it?
So I don't have the answer to this question, but I tell you what Ron Rivest, the guy from RSA, and his student in the center did. They did the zero knowledge stuff. Okay, so how to deal with the data without revealing any information. That's the only thing that I can tell you what they were doing in the center. Actually, they did something interesting. There is a lot of theoretical results in this. But what they did, they built a system, a real software system. You are only interested in this case in questions that are NP hard to answer. Otherwise, that's not interesting. So they actually, what they did, and I try to give you a short answer, they basically built a system. It is not interactive zero knowledge proof, a system in which any NP-hard problem that reduced basically to circuits problem, once they have it, they get some key. Once you have this key, you can answer the question. For example, you can send your DNA to a company that you do not trust. But you have to send to them because they have the power, computer power that you don't have. They ask the question, is there Hamiltonian path in some biological network of your DNA and so on? They give you an answer without them learning anything about your data, but you actually getting an answer. So I don't know if zero knowledge is one of the ways to do it, but I understand that the question is important, and thank you for actually mentioning it. That's all what I can say at this point.
Question about this graph compression.
Mm-hmm.
So there is this minus n log n term, and so this first term can be linear, can be big O of n if the graph is very sparse. So what happens then?
So yes, the first term is anxious to entropy, so it grows like n squared.
Yeah,
the second.
So
when P, you want to do it most likely for connected graphs. I explain in a second why. So for connected graph, P should behave like log n over n, not 1 over n. I tell you later in a second why. Then the first term is actually n times log square n, and the second term is minus n log n. And these two terms are very similar. That's why it is important that you try to do to the best of ability to match the second term. Now, why not 1 over n? Because the graph has isolated nodes then. And when you have isolated nodes, my theorem doesn't work because automorphism is not equal 1 anymore. There are symmetries. You need a new theorem. Why not you figure it out? I don't know the answer to it. Thank you.
Okay, Petteri Kaski, Aalto University. Thank you very much for the interesting talk. I would like to ask you, what's your opinion of the algorithmic dimension to this theory, in a sense? I mean, you have now this information theory sort of driving that you ask the correct question and so forth, and then you end up, for instance, with the graph compression algorithm. But what do you think about the time complexity of this theory? For example, if you look at your measure of graph similarity now, of course, it's graph isomorphism, which we know in general. I mean, it's not known whether it's polynomial.
Exactly. So this is a very good question, actually. I have a discussion with your colleagues here about a little different problem that I think I will answer in some sense your question. So these days, the database is so huge that you do not have access to the whole database, most likely. You actually, what you need to compress it. But when you compress it, you would like to do search in a compressed database. So I would reformulate your question, if you allow me, the following thing. I would like to do the following. I would like to do two things at the same time. I would like to get the best compression and match the best time complexity of a search in the compressed database. Do we have algorithms like this? My understanding is people are working on this, but that's what we're actually in the center also discussing. How to do efficient search and efficient compression simultaneously. So maybe somebody knows, I don't know answer to this question. And first of all, I would like to understand what are the limits are.
Regarding the joint string complexity, it seems similar to Lee and Vitani's work on universal compression distance and compression-based clustering. Is it somehow, so if you instantiate so they use Kolmogorov complexity in theory, but they use some compressor in practice. If you choose the compressor to be sort of Markov or sort of subword based, is it equivalent or is it fundamentally different?
I don't think so. I know Vitani work. I don't think it's similar. It's again, this problem I have a different solution. That is one possible solution. We use joint complexity. Because we were able to analyze it precisely and actually works very well for the application that we have. So I understand that the other was used for music and for some other cheaters, and so on. It's a nice work, but I didn't see enough analysis there to get me very excited, but it's me, okay. So in this case, we were able actually to get the right answer and apply it to real problems. Once in a while, I would like my theorems to work in practice, and I'm still dreaming about it.
Okay, let's have one more question, and then further questions can be addressed to Wojciech outside the door. So one more question, if there is one. Okay, maybe everyone just wants to get to the cocktails, and again we can continue the discussion in person after this session is over. So let's thank Wojciech again.
Thank you very much.